If S matrix, this matrix S, is a symmetric and second order tensor, you, the first thing that you have to keep in mind is that the S is symmetric matrix. This equation should be satisfied. Actually, S is equal to lambda I, or in other words, S minus lambda I is equal to 0. Actually, this is to project the second order tensor in principal direction. In principal direction means that you have to project it in lambda. So this identity matrix, you know it, I, the identity matrix, and this is the way we use to obtain the eigenvalues of S. If you remember from linear algebra, S minus lambda I is equal to 0. For example, if you have some matrix like this matrix, okay, it is symmetric, you see, right? It's symmetric. So if uh, you calculate the determinant of a minus lambda I, which is the same thing here, s minus lambda I, the determinant, if you just calculate this determinant, you will come up with this equation. And from this equation, you will find the values of lambda. So those are your eigenvalues. So the characteristic equation will be a polynomial equation. This is the uh, polynomial equation is lambda cubed minus is lambda squared plus uh, second invariant times lambda minus third invariant times I is equal to 0. So interestingly enough, the matrix S, this matrix S itself satisfy uh, its own characteristic equation. So it means that if you put S instead of lambda, it also satisfies equal to 0. And this theorem is called Cayley-Hamilton theorem in algebra. In linear algebra, if you go and search for it, it is the Cayley-Hamilton theorem. So it means that uh, either eigenvalues or the S itself will satisfy this equation, this polynomial equation, which is constructed by the invariance of S. The important thing about this Cayley-Hamiltonian is that if you keep this S cubed in the left hand side and take everything to the right hand side. So from here, I keep this to the left hand side and take these three terms to the right hand side. I will get this. And now you see that your S cubed is a function of uh, S squared and S, and also identity matrix. So actually there is no need to calculate the S cubed. In fact, the theorem of Cayley-Hamilton says it is true for any power of S greater than 3 as well. So S to the n, where n is greater or equal to 3, can be expressed as a linear combination, like this linear combination of S squared, S, and I. Up to this point, we did a very short summary of second order tensor properties, and this is what you will see in the Pope's book, the Turbulence book, also in the appendices of that book. The composition of second order tensors, the fact that the second order tensor can be rotated, and the existence of principal axis, which can be generated using eigenvalues and eigenvectors, and the existence of invariants for second order tensors, which do not change with respect to rotation. Those are all fundamental notions of linear algebra that we need frequently when we are dealing with turbulence models. But the question is why all of these is important to us. For example, let's say somehow you proposed a new set of equations and you claim that this new set of equations that you propose, when you solve them together with Navier-Stokes equations, they will mimic the certain properties of turbulence. For example, diffusion, or all the properties we made a list in last week's. The question is okay, that's nice, and you claim that physically this set of equation will mimic turbulence. Is there any extra second order tensor in this definition? If yes, what kind of invariants do they have? If I write the tensor that you proposed in another coordinate system, will it completely change or not? That's why the turbulence modeling is very combination of mathematics and physics. So with this part, now we completed the introductory mathematical part, and starting from this point, um, we will discuss more physics related to flow equations. And first of all, a summary of governing equations that are written in index or indicial notation. I will show it to you. Biraz da çay içelim arkadaşlar. Is there any questions?
No hocam.
No, I just need to study on it.
A study. Yeah, you have to study.
Yeah.
Okay. So let's go to the physics. So I'm not going to derive all of the equations. You've seen all of these equations during your undergraduate studies, probably, not 100%. So I will just write them in here as a continuity equation, which is a scalar equation. You know that in differential form, you can write it as d rho dt plus d dxj of rho uj is equal to 0 in general. So we have already discussed about uh, physical parameters or variables that are being either scalars or vectors or tensors. Equation that governs those physical variables can also be characterized as a scalar or vector or tensor equation. This continuity equation is a scalar equation. How do you know that? We see some indices like this index in here, J, okay? Why it is not a vector equation then? Because you note that J is a dummy index here. See, it is repeating J and J. So when we have dummy index, when we have two of these J's, it says that it's just a notation that indicates summation. So what do we mean by summation? We mean like this: d dxj of rho u j is nothing but d dx1 rho u1, d dx2 of rho u2, and d dx3 of rho u3 all summed up. They are summed up. So this is not a vector. This is just a summation. It does not represent any physical meaning. That's why we call it dummy index, this J. Whenever you see a repeating index, it says that you have to do summation over these indices. We also call this as replacing index. There is no free index or non-repeating index or non-replacing index. The only thing that you have in continuity equation is a dummy or replacing or repeating index. Once the equation does not include any free index, so do you see any free index in here? No. Once it is like this is called a scalar equation. In other words, it only represents one single equation. Although you have x and or also u are vectors, okay? So this x and u, each of them are vectors, but they are summed up. They are summed up as you see in here, and there will be just one equation. Momentum equation is written as a single equation. You remember it as a note, as an index notation. We wrote it as a single equation. But that single equation, in fact, represents three different equations because it includes some free indices. So most of the stuff that I'm going to speak about is restricted to incompressible flow. And when you start speaking about compressible flow, equations need to be modified a little bit, meaning that in averaging techniques, while we are doing statistical averaging, it needs to get modified a little bit. But main characteristics remain the same. In order to understand the concepts, we will first restrict ourselves into incompressible flow region. So this equation, this continuity equation, is valid for incompressible and compressible flows. And if you write it for incompressible flow, you can have such an equation in here, incompressible flow. So first of all, the time derivative of the density d rho over dt plus, mm, okay, you take this rho, this density outside of the differentiation, so it will be let's say uj d rho dxj plus rho duj dxj equal to 0. And when you combine these two terms together, it's actually making your substantial or material derivative of density, which is the capital D rho over dt is equal to 0. So uh, in here you see that material derivative is the time derivative plus the spatial derivative. In other words, at a frozen time, the density is constant everywhere, means spatial, and at another time also it is constant. So it means through time is also constant. So you will end up with um, rho duj dxj is equal to 0. Rho or density is not 0, so duj dxj will be equal to 0, or in vector form, del dot u is equal to 0. So again, in here you see repeating or replacing index. It means that it is just one equation, and it is a summation of these three. So u11 plus u22 plus u33 is 0. So du1 dx1, we just show it by u11 for simplicity in here. So del dot u is called actually the divergence of u is equal to 0. So what do we mean by divergence? You might remember it from uh, fluid mechanics course. So when divergence of u is 0, we call this as a divergence free flow. So divergence free flow is actually nothing but an incompressible flow that satisfies the continuity equation for you. So as another example, we just talked about the continuity. Now let's say we have a momentum equation. Your momentum equation, we said that it's not anymore a scalar equation. Why? Because it will include some free indices. Where are these free indices? You just see these free indices. So for example, in this term, you have j and j as repeating, but this I is a free index. In here, in this term, you have sigma ij over xj, so j and j is repeating, but again, you have this I as a free index. So, um, this sigma ij that I have in here, let me clean this to see it better. This sigma ij that I have in here represents all the stresses that I can have inside the flow. So it could be a viscous stress, could be a normal stress, a like pressure. Normal stresses, I mean pressure. And if the flow is turbulent, it could be even turbulent stress. So the turbulent stress is called Reynolds stress as well. So this is generally a second order tensor. This sigma ij is a second order tensor. You see I and j together, so it's a tensor. If you look at every single term one by one, what are these terms? D rho u I dt. So it has one free index, and it is nothing but the time gradient of rho ui, right? And rho ui is a vector. ddxj of rho ui uj. As we said, j is a dummy index, but I is free index. It should be consistent in every term in the equation. So each term should have this free index within. As you see, this first term has I, second term has I, third term has I, and fourth term also has this I free index inside. So it will be consistent. Then you have actually this ddxj of rho ui uj is some special gradient of rho ui vector. As you see, there is this rho ui vector in here, and there is rho ui vector in here times uj. So you have to note that in the second term, let me again clean it so you can see it much better. I'm talking about this second term right now. Talking about this term right now. Rho ui uj is a second order tensor, right? Because you have ui uj. When you take a derivative of this tensor with respect to this vector xj, it will become what? It will become a vector. So you have a tensor, you take a derivative with respect to vector, so you drop the order of that tensor by 1. It means that tensor will be a vector. So this will be a vector. And the same holds for sigma ij. So sigma ij is a second order tensor. You are taking the derivative of this with respect to one vector. So the answer to this term is also a vector. For the incompressible flow, when you have a constant density, you can write the momentum equation like what we write in here. So rho times dui over dt plus uj times dui over dxj is equal to dxj of sigma ij plus rho gi. Rho gi is just a vector of body forces, the forces that are exerted on the body, like electromagnetic forces, um, gravitational forces, and etc. Do we have any questions?
No.
So this equation at the bottom, this equation here, this equation is what? Is it a scalar equation, or is it a vector equation or tensor equation? I need an
This is a
answer.
vector equation.
Yes, this is a vector equation. As I said, all of the terms will give a vector, so this will be a vector equation. It means that it represents only uh, one single equation, but we have I as a free index equal to 1, 2, and 3. Okay, so it represents, it can take 1, 2, and 3. So this equation actually represents three different momentum relations combined all into a single line equation. And uh, you again, you have to note that um, this is uj times ddxj of ui, and the actually duj dxj is nothing but continuity, right? So the continuity says that this is equal to 0. So don't get confused. It has to be a free index in here. So dui dxj is actually your velocity gradient. Okay, we've talked about, let's say, we've talked about continuity and momentum. So let's put the energy equation as well in here. These are all the equations that are needed to represent the flow. The energy equation says that your total energy, which is okay, what is it? Energy is it a scalar, or is it a vector, or is it a tensor energy? Energy, come on. Energy is yeah. The total energy, which is shown by E0, is a scalar. It's equal to your internal energy. I'm showing it by E. So this is my internal energy plus, actually, internal energy, you remember from thermodynamics, it's equal to CVT. Okay. Plus half of UI. So as you see, you have a repeating index, so it means that it is a combination. If it's a summation. So what do we call this? We call this as kinetic energy or kinetic energy. You remember it from thermodynamics, right? Plus something else. So this something else is any other types of energy. It could be a potential energy or whatever. We don't care. The total energy should be conserved according to the first law of thermodynamics. And conservation of total energy level of the fluid says that the total energy can only be changed through heat transfer or work interaction. So what now we want to show it in uh, let's say mathematical terms. How to show it? Okay, the total energy change that we have in the left hand side, we are just put it here, is composed of the energy change in time, so change in time, plus the energy change in space, spatial change of the energy. So what we are using is rho times the total energy. Okay, so the thing that is changing is rho times the total energy. It means that the total energy of a specific uh, amount or mass that we have. So if you remember in the momentum equation, you had rho ui that was changing and uj was multiplied by that. So in here you have rho e0 that is multiplied by uj. So your rho e0 is changing through a space and equal to, if we said that what changes this energy, either work or some heat. So we write the work as uh, let's say work of body forces or work by the shear forces or stresses, not only shear but normal plus shear, which means the stresses work. And this is the value of the heat flux in space. This equation is should be an scalar equation because energy is a scalar itself. So the first term, if you look at this, it is a scalar. So there is no index in the first term, and it should be consistent in all other terms. That's why when you put dxj, you will put one uj inside. In all other terms, we have dummy indices, meaning repeating indices. So left hand side and right hand side are consistently written, and there are no free indices. So the energy equation is a scalar equation. So again, if you just consider incompressible flow, you can take out the density and the energy equation will be written like this. And we call this as equation 1. If there is no question, we can continue. These are all stuff that you know, but right now we are showing them in initial notation because we have to save some space since we are writing too many equations from now on. Okay, we saw the general energy equation in here. E0 is E plus half of ui. So it has two terms. Can I actually derive a separate equation only for conservation of internal energy and then one separate equation for the conservation of kinetic energy? This is the question right now. I want to separate energy equation into two. Why do I want to do it? Because energy, um, the internal energy is equal to CVT, as I said. So it has some temperature inside. Okay. If I want to write an equation to get only the temperature distribution, I have to find this CVT equation. Because from continuity and momentum equation, there is no temperature there. Temperature is only inside the internal energy. So it's perhaps it's a good idea to write two different equations uh, for internal energy and kinetic energy. Later, we are going to write governing equation for turbulent kinetic energy. Whatever that is, we call it turbulent kinetic energy, we call it K, and that is the same K as that appears in K epsilon and K omega turbulence models. Some of you, or maybe all of you, are familiar with these K epsilon, or at least have heard about it. So this K is the turbulent kinetic energy. All these models solve governing equations for turbulent kinetic energy. So they have some equation like the one we just gave for total energy in here for only turbulent kinetic energy. So we will derive those later. So my aim right now is to write two different equations like this that I have in here, one for internal energy to actually come up with some temperature distribution, and one for this kinetic energy. So how do I derive it? Well, I will start from uh, momentum equation, conservation of momentum equation. Now note that I want to find the mechanical energy, meaning that I want to find uh, an equation for kinetic energy right now. So if I start from momentum equation, what you see in brackets in here, this is only your momentum equation. Okay. I will start from momentum equation and multiply this momentum equation by ui. First of all, I need a conservation. Why do I do this? Why do I multiply it by ui? Because if you go back and you see this, it is ui times ui. In momentum equation, I actually wrote the conservation of ui. So if I multiply ui by the conservation of ui, I will come up with ui squared. That's why I need to start from here. So I multiply momentum equation with ui. So I'm not going to, let's say, write all the terms. The first term, for example, ui times this term, rho dui dt. Okay, rho is constant, so ui times dui dt will be equal to half of dui squared dt, which is nothing but d of half of ui squared. So I just constructed this thing that I have in here, half of ui squared in momentum equation times ui. So I just constructed the first one. You will just follow and you will just try to multiply ui by the second term and this term as well. So if you keep doing this for other terms, the dependent variable will be no longer ui. It will be 1 over 2 or half of ui squared. Everything will be converted to this, which is your kinetic energy. The conservation equation for the kinetic energy, um, that we call it mechanical energy, and for incompressible flow will be this equation that I have given to you in here. So this ui um, d dxj of sigma ij, actually you can expand this. I will write it in here. It is d dxj of sigma ij uij, okay, minus sigma ij d ui dxj. So this sigma ij is a second order tensor. This is velocity gradient tensor. So you have a multiplication of two second order tensors in here. And as we said, this F is the body forces like what you have as rho gi and etc. So uh, when you expand it, you will come up with the last equation that I've shown in here, equation 2. So now it's enough for the mechanical energy. So we will leave the mechanical energy here and let's look at this internal energy. So let's look at the thermal or internal energy. Tell me if you get tired or if you get confused. Okay, how do I uh, come up with the internal energy? It's obvious that it can be obtained by subtraction of mechanical energy from total energy. So you see in here, if only there are two terms, if I write equation for this and I write equation for this, if I subtract the mechanical from the total, I will come up with the internal energy. That's what I do. 1 minus 2. So again, as an example, the first term in 1 minus the first term in 2 will give me the first term uh, for the internal energy. So I will subtract and I will write it. So this will be the equation 3 would be the, let's say, equation for the internal energy. And I said internal energy is CV times temperature. So if I put everywhere inside, E is equal to CV times temperature, CV time temperature. Then what happens? It somehow gives me, if I can manage to solve this equation, this partial differential equation, if I manage to solve it, it will give the temperature distribution as well to me. And let me check. Okay, I will give. Okay, the final equation that I need right now is the entropy equation because um, so far we've talked about continuity, we've talked about the continuity, the momentum, the energy, and then inside the energy, we said, okay, total energy, kinetic energy, and also internal energy. So we talk about all of these. The only thing that I need is the second law of thermodynamics, which is the entropy. So in terms of including all relevant physical mechanisms that are happening in physical world, only I need the entropy, and then it will be everything will be fine after I get the entropy equation. So let's have a look at the entropy equation, and then we can stop. This may be relevant for some flows and may be irrelevant for other flows. But to keep things general, for example, in order to estimate the loss generation in turbo machine, a turbo machine, for example, an aircraft engine compressor, you either build a test facility and try to measure total pressure losses. The total pressure losses are related to the entropy generation. Or if you cannot do the test, if you can write the governing equations for entropy, which is the generation and destruction of entropy, and you somehow can solve that equation, if all terms are solvable, you can actually theoretically find entropy generation, which means you can theoretically find loss generation. So either theoretically or uh, by tests experimentally. It sounds nice, but it's very difficult to do these theoretical approaches in turbulent flows because there are many unknown terms in the entropy equation. Similar to the temperature and density and pressure, the entropy is also an scalar. And the entropy equation is written in here. So the first term is the generation of entropy through time. This is the convection of entropy in a space. and we call it as advection. This is advection, and you see this term Q over T, the spatial variation of Q over T, and also you're seeing this term at the end. This is the irreversible entropy production. So this phi is always greater or equal than zero because of the second law of thermodynamics. And this is due to actually heat conduction and viscous heat generation. Heat generation due to friction, of course. When there is turbulence, uh, actually we want to relate this relation to turbulence. So this is how we justify this. You have a turbulent flow, so it means that you have some fluctuations in the flow field. And these fluctuations will generate entropy. When you write this equation, the equation for entropy, equation 4, for turbulent flow field, on the right hand side, you end up with very complex terms. Complex meaning that they're complex correlations like pressure fluctuation times Reynolds stress. Like you have some pressure fluctuations times u prime. Okay, things like this, and we do not know what they are, and they are difficult to measure because it's not very easy to measure pressure fluctuations. How do you want to measure pressure fluctuations? You can try to measure it with some high frequency response probe, a fast pressure transducer, but when you uh, when you insert it in the flow, it would change the turbulent characteristics inside the flow. So the pressure fluctuation may not be the flow pressure fluctuation. What you're measuring is nothing, is not related to the real case. So the question is, can you measure pressure fluctuation optically? For example, when you're doing PIV, will it give you some details about the pressure as well? You have to think about it. The other path, the other way that you might be able to calculate these complex correlations between pressure and velocity is to do direct numerical simulation. This direct numerical simulation, we just touched it in previous weeks, but it does not involve any modeling. It directly solves the flow. So in DNS, you have to resolve all eddy sizes from the smallest one to the biggest one. But the problem is that it's very, very expensive. And also it is limited to very, very low Reynolds numbers. So this equation, the entropy equation, um, completes all the equations that we deal with when we want to simulate a fluid flow. We want to obtain a distribution of parameters that is our objective when we are solving these equations. Distribution of velocity, distribution of pressure, density, temperature, and also entropy. Of course, the flow field could be very simple, as in laminar pipe flow, or it could be very complex as a turbulent flow in a multi-stage compressor of an aircraft engine.